things on the table as confirmed. Okay. But basically, what we wanted to understand with regard to trees was that please mute. Please mute. Okay. What we wanted to understand as far as trees was concerned is that it's part of data structures together with how say graphs we are going to also look at those ways. It's a linear type of data structure which basically will have access to data sequentially is for tag, arrays, linked list, queues. That's for linear data structure. And when you are dealing with for trees, we are looking at it in terms of nonlinear data structure. So that's the main thing. So we have graphs, we have trees, which basically form nonlinear data structure, whereby in this case, we can only access data non-sequentially. Okay, that's what we looked at the last time. Then went on and on to be able to understand the tree traversal, which I'll skip to that. So these were some um, practical examples we can look at where we can apply trees, the hierarchical administrative structure, the product information categorization, the student information categorization in a university. Let me deactivate the pip sound. Okay, so yeah, that's good. And then we also saw what a tree is, and we saw that for us to be able to get a tree, we need to be able to know that a tree will have at least one node, and that node should be designated as the root node. If it has multiple nodes, then we should have one of them being a root node. Now, if I disconnect the root node from the remaining nodes, I should be able to have what we refer to as what? A forest. And that forest is basically defined as a set of disjoint subtrees. Okay, like you can see what I'm doing now. So once the root node is disconnected, okay, then I can easily be able to have a set of disjoint subtrees. If I have a situation like that, then I can be able to call a structure a tree. Unlike this situation, whereby this particular just a second. Unlike this particular one where we have E, okay, which is basically in this first disjoint subset, also in this second disjoint subset, we cannot classify this structure as a tree. So that's the main thing on the table. Are we good? Now, the next thing we need to be able to look at has to do with the various terminologies or some definitions of tree. So parent, we saw that here, this is basically the parent of B, C, D. The B is also the parent of J, H, I. And then in terms of siblings, we can say that J, H, I are siblings, okay? Then we went on to look at things like the terminal nodes, which is the same as the leaves. So here, J, H, I, E, F, D are what we refer to as terminal nodes, which we can also refer to it as what leaves, or we can refer to them as what external nodes. And if it's not a terminal or external or it's become an internal node. So this B, C, A are what we refer to as what internal nodes, or we can also refer to them as what non-terminal nodes. We can also refer to them as what non-external nodes. So basically, these are the various things we need to also know. Then we also saw the level of a node. So we saw that the level is actually determined from the root node as level 0, followed by B, C, D in level 1, J, H, I, E, F as level 2. Then we realized that for us to be able to determine the depth or the height of a tree, we need to be able to know the maximum level a tree can take or a particular node can take. In this case, the maximum level is 2. So in that case, the depth of the tree or the height of the tree is 2. So those were some terminology we saw. And then, yeah, the rest, those of you didn't join a class, you can actually read on your own. we went to look at a binary tree. So for binary tree, we realized that a binary tree is any tree that has a maximum of 2 children. Okay, so you can either have a 0, you can have a 1, or you can have a 2 maximum. Okay, so that was where the definition comes from here. So it is basically a tree that has at most 2 children. That's it here. Then we went to look at some examples of trees. We saw that this is a typical example of a binary tree. This is also a typical example of binary tree. This is also a typical example of binary tree because each node has a maximum of 2 children. Okay. Then we went to look at a strict or proper binary tree. So for strict or proper binary tree, we said that it should have max 2 nodes or 0 nodes. So for strict or proper binary tree, each node should have 0 nodes or 2 children. That's it. Then we went on to also look at what we refer to as the complete binary tree. Here, all the levels are supposed to be completely filled with the exception of the last level, which when it's supposed to be filled, it should be filled at leftmost as possible. And that's what we saw the last time. So we realized that this example is not a complete binary tree, but this is a typical example of a complete binary tree because the last level, if it's supposed to be filled, is filled from the left, coming to the right. Okay. Then we have the perfect binary tree. From the word it sounds, perfect means that all the nodes are supposed to be perfectly filled with 2 children. That's it. Then we saw this thing. Those of you who didn't join the class, please refer to your colleagues how you can be able to prove when you are given 2 to the power h plus 1 or minus 1, and how you can be able to make the n, which basically is the number of nodes from that particular jurisdiction. So we need to be able to follow up with the colleagues on that. Then we came ahead to also look at what we call the ADT, which we realized that for ADT, all we need to be able to know is how we can be able to get the various nodes in terms of the instances that have to be there, and then how the operations also work on them. So empty will return that the tree is empty, there's nothing inside. Then we can also look at the other one, which basically is the size, which will tell us the size, the number of nodes in it, or the cardinality. And then we look at a pre-order, the in-order, and the post-order. That's also another thing we saw. Then we saw the pre-order, which basically we're going to look at shortly. So we start with a tree traversal, how many ways we can be able to visit the nodes in the tree. So in the in-order, the main emphasis has to be the root node. The root node is the focus of discussion here. What does it mean? It means that for us to be able to have in order, so please, this is still a recap. We saw it last week, okay? So that's why I'm rushing through it. It's not like I'm teaching it from scratch. So for the in order, our main case is that the root node is the one under consideration. It's supposed to be in the middle. So we target the left order, the left subtree, which is this, followed by the root, followed by the right. So the root is supposed to be in the middle. It's supposed to be the one to be visited in between the left subtree and the right subtree. Can you mute, please? So in this case, what are we saying? All we are saying is that if I want to be able to visit the nodes in this tree, then, oh, guys, please mute. Then what I have to do is very simple. I have to pick the left subtree first. In the left subtree, I'm going to start with the leftmost, which is the D. Then I go to the B, which is the root in this case. Then I come to the E, which is the right node. Once I'm done with the left, I have to go to the in-between, which is the root node. Then I can now come to the right. For the right, I start with the leftmost F. Then I go to the in, which is the C. Then I come to the right J. Now the end, this is what you're going to have. D, B, E, A, F, C, J, right? That's it. Then we saw the pre-order. Pre means before. So emphasis on the root means that the root will be the first node to be visited. So at the end, I'm going to start with the root node A. When I start with the root node A, what do I need to do? I need to now go to the left before I come to the right. So I'm going to start with the root A. I come to the leftmost. Once I'm at the leftmost, I see another root node here, which is the B. Then I come to D, then I come to E. Then when I'm done, I go to the rightmost. Rightmost, I start with the C, which is the root node, come to F, then hit G. Can you see that? So then I'm going to have A, which is the root node, coming to B, coming to D, coming to E. Then I go to the C, go to F, come to G. That's it. That's not a pre-order tree traversal. Then the last one we saw was the post-order tree traversal. The post-order tree traversal, the algorithm works in such a way that post means after, so the root node will always be visited last. Okay, so we're going to start with the left. You're going to go to the right. Then go to the lastly hit the root node, which will be the last one. So what do we have? I'm going to pick the leftmost, and at the leftmost, which is the left subtree, I pick the D. I go to the E, then I go to the B. Please hold on. Then so the post order, you start with the leftmost, you go to the rightmost, then it hits the root. So at the leftmost, right, that's the left subtree. I start with a D, then I come to the right, which is the E, then I go to the root, which is a B. Then when I'm done, I come to the right. I start with the left F, go to J, go to the top C, which is the root node. Then when I'm done, I finally will end with the root node A. Work is done. So this is what you're going to see. D, E, B, F, J, C, and lastly A. Is there any question on this? Awesome. So for the binary tree, we also came to see how we can also delete the node. So this is the last thing I think we did. Then we ended up with the application, the work was done. So with the deletion, we mentioned that deletion can be done in three main ways. So first thing we need to do is that we need to identify the node, which is the parent of the node to be deleted. So if I want to delete a particular node, my main focus is to be able to find out if there's any other node that is acting like a parent. Okay. So what do I need to do? I need to first identify that node. Once I identify the node, then I can now go ahead to be able to look at any of the steps involved in deleting it. And how do I do it? Come here. The first case, I want to be able to delete a node that has no children. So this is the node to delete, right? The -4. First step is to be able to identify the parent. The parent is 2. We good? Now, once I identify the parent, which is 2, work is done. All I'm going to do is that I am now going to set this particular parent to now here. Good. So when I do that, work is done. It means that the 2, which is the parent, will be pointing to now, meaning that the 4 is no longer in existence. So that's very straightforward. The next one on the table is if I want to be able to delete a node that has 1 child. So I want to delete 18, okay? And basically 18, I have to first identify the parent. The parent is what, 5. Now for the parent, which is 5, sorry, please hold on. Please not happening. Okay, so in that case, all I'm going to do that is I have to first identify the parent, which is 5. When I identify the parent, then I'm going to link the parent to the child of the node to be deleted, right? Because it has 1 child, 18 has 1 child. So all I'm going to do is that I'm going to link the 5 to the 21, which is 21 as a child of 18. Once I do that, then 18 is gone. If 18 is gone, work is done. I can now be able to say that the final part after the deletion will be 5 pointing to 21. That's all. Are we good on that? The last thing on the table has to do with a node to be deleted having 2 children. Please just a second. Okay, so we continue. So I was saying that the node to be deleted has two children. So first thing is identify the parent of that node. This case is 12, the parent is 5. Then what do we have to do? The algorithm says that your focus should be able to find the minimum element in the right subtree. The right subtree is this guy. So find the minimum element. The minimum element here is 19. Now, once I identify the 19 as the minimum element, the next thing I'm going to do is to be able to what? Replace the node to be deleted with it. So I'm going to replace this 12 with a 19. So now I'm going to have this 19 here, which is going to be used to replace the 12. So I'm going to have 19, 19. Then when I'm done, all I'm going to do is I'm going to set this 21 pointing it to now here. Once I do that, then the whole of this will vanish. Work is done. So if it does the case, then I'm done. So what does it mean? If it means that if I'm deleting a node that has two children, the algorithm says that identify the parent of that node, right? When I identify the parent of that node, I need to be able to focus on the right subtree, which is the right child, okay, of the node to be deleted. So my focus has to be on the right. Once I focus on the right, I need to be able to identify that, okay, fine, is there a minimum child there? If there's a minimum child there, then that particular minimum child is going to be replaced with the node to be deleted. Once I replace that, then I'll be able to set, in other words, delete the node, which is now the minimum child. In other words, this guy was only one node, okay? Like 21 alone, then work is done. I'm just going to replace the 21 with a 12 here. And what am I going to do? I'm just going to get rid of this by pointing this to that. So that here will be 21 and this guy will be now. That's it. But
Sir,
because there's a minimum child here 19, that's what I did there. Yeah, please go ahead.
sir, please, what if there is no minimum child there?
If there's no minimum child, there's only one child. Like the example I gave, 21 here, then here will also be 21. Okay, it means that this 21 will go away.
Okay. So
Please,
it will
does it
be
make sense?
so the 19 and 25 will move up.
No, that one is not there because you are saying there's no minimum child. So it means that this 12 is pointing to only 21. There's no 19, there's no 25.
Okay. Sir, please, can you solve it here so that I will see what you are
Oh,
talking about?
I'm trying to ask. Hello, can you hear me?
Yes, sir. Sir, it's okay.
That's a question, right?
Yeah.
Okay, so if that's a question, then what I'm trying to say is this. Then basically what you can do is, because this 21 is the only one here, it's still within the minimum. So the algorithm will pick the 21 and replace the 21 with the 12.
Okay.
So that at the end, this 12 will no longer be 12, but will be 21.
21.
Then the 21 will now point to now. So this will go away.
Okay.
Okay.
And then this will be now 21.
Okay. So the 21 will not be having children.
No, it's from the
Okay.
question you gave, the 21 is not having children.
Okay. Okay. Thank you so much.
Please do you understand?
Yes,
Okay.
please.
Please,
Okay.
anyone else? Yeah.
Please, can I go ahead?
Yes, please go ahead.
So, please, my question is, what if at the last subtree, the right one, the last two were 19, 19? Like, what if they were the same? How will you determine which is the minimum?
Please, which one?
So, let's say we were referring to the subtree that's 21, and we were looking at its minimum, the children for 21, and then they happen to be the same, like 19, 19 instead of 19 and 25. What do we do in that instance?
Okay, so if I get you right, this is 19, this is also 19, right?
Yes.
Good. So that's a very good question. That's a very good observation. So in that case, and normally we don't get there. Normally the nodes are different, normally. Okay. The reason why the nodes have to be different is that it depends on the value that's attributed there. But when you have it in that way, remember the focus is on the right subtree, right? So once we are here, this is 19, this is also 19. The minimum is 19, 19. So randomly, the algorithm can pick the rightmost node and then replace with this. And then now this will be pointed to now. So the focus will be on the right. Okay,
Thank you, sir.
you're welcome. But normally we don't run into that. Okay. Okay. So the applications we already looked at, and the Raka data representation, database indexing, game trees, how you can be able to play with chess, and then you are playing with a computer, and then the computer can win you. It's able to know how the moves and other things, right? Especially representation, network routing tables, other stuff, with all the things. Then we came across the assignment, and this assignment Wednesday, when you have the tutorial, so at least we can be able to go to goal. That was what we saw last week. Now we can now go ahead to what we have today. Okay. So I spent some time there. I didn't want to do that, but it's fine. So now let's see how we can handle today's thing. Okay, so today our focus is this on graphs. Okay, and graph 2 is also an example of a type of the nonlinear data structure. And basically, this nonlinear data structure, what we are talking about is you want to be able to access data non-sequentially, not like the linear one. We can access data sequentially, like the queues, the stack, and then the linked list stuff, right? So, but this one, data can be accessed in a non-sequential manner. So let's look at the concept of graphs quickly. And then, so when you talk of a graph, it's basically a nonlinear data structure, which basically is used to, so I can see your screen. Okay, please, can you all see my share screen?
Yes.
Yes,
Yes, sir, I can see.
Okay,
Yes, I can see.
that's fine. Good. So a graph is a nonlinear data structure, which I've mentioned, which is used to model and represent a wide variety of systems in real world, right? So that is the main thing. So just like a tree, you can also have the graph consisting of what we refer to as nodes. But this time around, with regard to the tree, the graph, we refer to the nodes as what vertices, okay? And then the connections are basically referred to as what edges in graphs, okay? So basically, with regard to graphs, we're going to say that a graph is defined mathematically as a set of vertices, V, and a set of edges, E. Okay, so that's basically when we talk of a graph, it should be able to ring in your mind. But unlike trees, graphs will have no restrictions with respect to the connections between the nodes. This means that nodes can be connected in any possible way at all you can think of, right? One thing you have to also know is that when we talk of a tree, it's in fact a type of a graph, okay? Now, with regard to that, we can now be able to say that since a tree is a type of a graph, then we should be able to understand the fact that what type of graph would it be? So we're going to look at it surely and see the type of graph a tree will be in. Then that's what we have to also understand today. Now, a graph, as I mentioned, is basically an ordered pair of a set of vertices V and a set of edges E. Sometimes we can also refer to it as what? A set of what? Arcs. So that's another thing we need to also take note of. Now, in that case, once we have this, we can be able to go ahead and then say that if you have a particular graph, which is a Vn3 mapping to a Vn1, in this case, because there's no direction or arrow, we can also say that Vn1 will also be mapping to what? Vn3. When we see it in this way, then all that we are going to say is that this is an example of what? An undirected graph, which will be seen surely. Another thing we also have to know is that we should be able to know the origin or the source and the destination. So if I have Vn1 and Vn3, if Vn3 is pointing to Vn1, then Vn3 will basically be the origin. Then Vn1 will now be the destination. So these are things that we also need to be able to take note of when we are trying to understand the graph concept. So if you are trying to find out all the vertices, then we're going to be able to say that the V is going to be defined as a set of vertices V1, V2, all the way to hitting V8. Then if you also want to be able to understand the edges, then we're going to look at the possible pairs between them. So like, for example, this is V1, V2. vein 1, vein 3, vein 1, vein 4, vein 3, vein 7, all the way to the end. Okay, and this is basically an unordered pairs, right? Because we can move from vein 1 to vein 3, we can also move from vein 3 to vein 1. So a graph may also contain both directed and undirected graphs. So like this example is a typical example of the two main types of graphs you can think of, right? Directed graph, which will have the arrows there. And then we can also have the undirected graph, which will not have the arrows in the equation. So in that case, what do we do? All we are going to do is that we are going to be able to look at it in this way. How? We're going to be able to see that for us to be able to have an undirected graph, then we shouldn't have any arrows pointing or differentiating the origin and the destination. But for us to be able to have a directed graph, then we should be able to have arrows differentiating the origin and the destination. So for example, in this case, vein 3, vein 1, we know that vein 3 is the origin, vein 1 now becomes a destination. Please, do you understand now? And then, any question on this before I move on?
Sir,
Yeah.
please, for the relationship between V1 and V2, the arrow point partly, I don't know if it's a part point, but it points to V1 from V4. Sorry, and then it also points from V1 to V4.
Okay,
It's
we're going to look at that. We're going to look at that shortly. So we're going to go there, then I'll explain that to you, right? So we're going to have vein 1 going to vein 4, and I'm going to have vein 4 to vein 1. So there's a type of graph that's like that. So I'm going to show you no time when we move on. But basically, let me talk about this quickly. It's like you want to be able to move from, let's say you're on campus. You want to be able to move from distance education unit all the way to, let's say, your hall. Assuming your hall is probably at Equafo Annex A, let's assume, right? It means that from the distance education unit, you can actually be able to hit the roundabout, okay? Get yourself and route it to Equafo Annex A. Or you can use the first roundabout at the main gate, then you can come to the second roundabout at the Equafo Hall main gate, and then you can now go all the way to Equafo Annex A. So that's it. So it means that here, if you have the arrow this going way, this going away, it means that it's not the same route you are using from vein 1 to vein 4 and vice versa. So it can be the other way around. That's it. But then you're going to hit the same destination. You're going to hit the same source. That's it. Please, do you understand?
yes, sir.
I can have vein 1 to vein 3 to vein 1, and I can have vein 1 back to vein 3. Then the arrow will be here. So it means that this one, the same direction I use is the same direction I'm using to go back. But this one, it means that I can use a different direction, which is different from the one I used to be able to get to my destination.
Okay, yes, sir, I see it.
You get what I'm trying to talk about, right?
Yes, sir.
Great. All right. So we come here. Okay, so this is weighted directed graph. Remember, I mentioned here directed graph. Another word we can use is what we call the digraph. Don't forget about that. Okay, and then we can have what we call the unweighted graph, and we can also have what we call the weighted directed graph. So when you talk of the unweighted digraph, remember digraph is the same as what directed graph. So I can call this an unweighted directed graph, or I can call it unweighted digraph. That's it. Now, when you talk of the weighted one, so for the weighted one, all we're saying is that they have different duration, different weights, different cost, different. So the weights can be cost, can be duration, can be time, can be whatever you can think, can be distance in kilometers or meters, whatever, right? So that's another thing we should be able to know. But in the case whereby we have no weighting, then we assume that the weighting will be constant, probably unity 1. That's it. Look at some interesting applications of graphs. Okay, so right now you'll be there, you go to Facebook social media handle, and you'll be there, and then there's a friend request, okay, or some suggested friend requests for you. Okay, so the tree structure is in such a way that you can be able to have it looping through your friends and then finding mutual friends of those friends, and then see whether they can make some suggestions for you. So once you are there, you see a suggested friend request, what do? You're going to be able to go into it and check who is this person. or you are there, you get a friend request, you want to be able to go into details to see who is this person. Then you check and you realize that that friend belongs to a friend of you. That friend belongs to a friend who happens to also be another friend to a friend of yours. You see, so that's a particular networking. So in that case, the graph architecture is able to help us to be able to know some interesting suggested friend requests for us to be able to. And that's a typical example we can see. Another one too, we can also see is how we can navigate on the World Wide Web, right? I can be here and I can be able to hit the University of Ghana web page, and I should be able to navigate myself to the student portal to be able to do registration. I can be able to navigate and come back to the home page or the landing page and do all kind of stuff, right? So that's also another thing that can also be on the table. And the last one, we can also look at the intercity roadmap, whereby even Google Map can actually help us. So it leverages more on the graph theory to be able to know the shortest possible path you can use, whereby there's less traffic congestion there. So it's also another thing that you can also leverage on. We have been using it, and these are all based on how the graph theory works. Okay. So some properties, I can have the directed one for myself here, then I can have the undirected. So in this case, what it means is that once I leave a destination, I'll come back and go back to that same page. So I give you an example like the home page, right? On the website, I can be able to navigate to all other places that can come back to the same home page. And here I can also navigate in different direction. And at the end, I can come back, or I can start with any other direction and I can come back. So that's it. Then a multi-edge or the parallel edge, right? So this is what I was talking about. Graph representing internet web pages. A page can have a self-link. Okay. So wherever I am, I can move across, and then I'll always have a home page tab that I click that will bring it back to the same home page. Now, the multi-edge or the parallel edge, it is an edge that occurs more than once, right? So graph representing flight network between cities. A pair of cities can have multiple flights running between them. So this particular one, I can move all the way from Ghana to Addis Ababa. Oh, sorry, Accra to Addis Ababa, right? Addis Ababa is the capital of what? Ethiopia, right? Or I can do vice versa, okay? In this case too, I can also do the same, and I can also make a journey back. So this is where the example was coming from I was talking about. So you can have here as a typical example of a directed multi-edge graph, right? Whereby I can move from here to this side. I can also move from here to that side. Or I can move from here to this side, or I can move from here to another side here. So there can always be different routes we can use to get to that destination. That's how the flight guys work. So sometimes if it is raining some way and they cannot be able to pass through the storm, they can hover around it with some nearest location that will not have any issues on that. So that's how it works, okay? We look at the properties of the graphs. So for the properties of graphs, in this case, I can be able to say that self-loop or multi-edges make a graph complicated to work with. And then if you're also dealing with a graph that's basically have simple graph, then we are saying that there's no self-loop or is no multi-edge. So that's a very example of a typical simple graph, right? So there's no complications in terms of the connections. So given the number of vertices in a simple graph, right, what would be the maximum possible number of edges that we can think of? So we assume that the number of vertices is known. Our main key thing is how we can get the edges. So we have, let's say, a typical example here. There are 4 vertices, V1, V2, V3, V4. And then in general, I can be able to have the cardinality or the size of that particular vein, which in this case we know is 4. So the size probably is n. Then I can be able to establish this particular relationship between the number of vertices, okay, in terms of its formula and the size of the edges. So I can say that in terms of the edges, I can have a minimum of 0 and I can have a maximum of this extreme n going to n minus 1, where the n here would deal with the number of vertices, in this case 4. This is for the case of a directed graph. For the undirected graph, then the formula will now be in this way. So let's prove it. Let's see how it works. In this case, I have 4 vertices. 1, 2, 3, 4. N is 4. So when I come, I'm going to have 4 times 4 minus 1, which is going to give me 4 times 3, which is 12. So the maximum number of edges I can have in this typical example will be 12. How? Let's look at it. So this is from here to here, 1. This is from here to here, 2. So in this case, between V1 and V2, we have 2 edges. Can you see that?
Yes,
Between
sir.
V1 and V2, good. Now let's look at between V2 and V4. That one to two edges. V4, V3, two edges. V1, V3, two edges. Then in the diagonal aspect, V3, V2, two edges. V1, V4, two edges. So in all, I'm going to have 12. Check it. 2, 4, 6, 8, 10, 12. This is a case of a typical example of a directed graph. The extreme case, the maximum you can have is 12 if you're having 4 vertices. What about we looking at it in terms of undirected graph? Undirected graph means that I'm going to have V1 hitting V2 here without any arrow. I'm going to have V1 hitting V3 without any arrow. The same applies. I'm going to have V1 hitting V4 without any arrow. V3 hitting V2 without any arrow. And lastly, V3 hitting V4 without any arrow. So if I do that, then at this situation, I'm halving it. So that's why we're going to have this divided by 2. So the 12 you had is going to be divided by 2, which is going to give you 6.
Yes, sir.
I hope that makes sense to you guys, right?
Yes, sir.
Okay. I think there's a please, you are moving a bit fast. Oh, sorry. Okay, I'll see what I'll do because I wanted to try and see whether I can finish some stuff together. But you say you're writing exams when?
On the 17th of next month.
Okay, so I can meet you next week, right?
Yes, sir.
Okay. So okay, now let's look at this. The difference between a dense and the sparse graph. For a dense graph, what we are saying is very simple. When you talk of a dense graph, it is where you have the number of edges in it is close to the maximum number of edges, meaning that we have too many edges when you talk of a dense graph. Okay, so in that case, we are going to say that if you have a dense graph, then basically the number of edges are so numerous or voluminous that you don't even know what to do. So basically, we are saying that with regard to the dense graph, the number of edges are very a lot. Now, how do we know that? So look at this. If you come back to this formula here, okay, once you're able to calculate and you know that there's maximum number of edges you can have based on the number of nodes, and assuming in this case, I can be able to say that with this undirected graph, okay, for example, no, let's say the directed graph, for example, I have 12 as the maximum. And then in real life situation, I did a count and I realized that the number of edges is 11. So we can actually say that it's actually dense graph because you have 11 against a maximum of 12, okay? And then even if you have 9 against maximum of 12, we can still confirm it to be dense, okay? Basically that. So we can use the threshold half to be able to look at it. Now, when we come to look at it in terms of the sparse graph, if the number of edges in it is close to the number of vertices, are you with me? So the number of vertices in this case we had was 4. And then let's say that we calculate the number of edges, and then we had, let's say 5, or let's say 3. We can say that this is a typical example of a sparse graph. Why? Because there is a very relatively less number of edges or arcs in the particular graph. Okay. The data structure chosen to implement a graph depends on whether it is dense or sparse. For example, a dense graph is represented with adjacency matrix. A sparse graph is represented with an adjacency list. Okay, so that's it. So with regard to adjacency matrix, adjacency list, we're going to be able to look at it surely, right? So simple part is easy to understand. If a path is simple, it means that there's no repetition. If a path is not simple, then it's basically going to be a walk, right? So a walk in which the vertices are repeated, in which the vertices are not repeated, right? It's called a path. If the vertices are repeated, we call it a trail, right? So a trail and a path are a little bit different. So with regard to a path, basically simple path, vertices are not repeated. For a trail, we're going to be able to say that the vertices are actually repeated. Okay, and that's it. So what do we have? So let's look at the walk set to be closed. Basically, what are we going to see? We're going to be able to look at the walk is set to be closed if it starts and ends at the same vertex, right? And the length of the walk number of edges is greater than 0, right? Which is very simple to understand. So sometimes you can call it a cycle, right? Because if you are dealing with a closed walk, it means that if I start with node A, I should go back and come all the way to that node A. That's it. A graph basically with no cycle is referred to an acyclic graph. It means that if I start at node A, I will route and I'll never come back and hit node A again. That's it. So for a cycle, which is the same as a closed walk, basically what I'm talking about, if I start from distance education unit, I should route and come back and end at distance education unit on
Sir,
campus. Yes.
please, can you take it a bit slow because it's like you're moving fast.
Oh, really?
Yes, please.
Hey, sorry.
Okay. How many of you think same?
Me too, I think same, sir.
I wanted to finish and then get something.
Same, sir. Me too. Same, sir.
Oh, really? Okay, that's fine. Let me come down to your level, right? Sometimes when I'm teaching, I forget that you guys are in first year. Sorry about that. Okay. Let's go again. All right. But we are on points, right?
Yes, please.
Yes.
Great. So we
Yes, sir.
mentioned about a simple part. For a simple part, what we are saying is the number of let me go back. Right. So a simple part, it is any kind of path whereby the vertices are not repeated. So a very example is ABFH. Okay, that's a very typical example of a simple path. Okay, so ABFH, none of the vertices is repeated. All right. Now, in the case whereby the vertices are repeated, that is where we are having what we call a trail. So for a trail, I can have A, B, F, H, E, B, A, D. B is repeated, A is also repeated. So that becomes a trail. Sometimes trial, anyhow. Yeah, I think trial should be the right. Sometimes you call it tree, anyhow you want to call it. Now, what we have to know, now, if it's in that case, then all we are saying is that if you have it in these two cases, then the main thing is that when I come to the close walk, okay, so a walk can be classified as a trail or it can be classified as a path, right? Basically, what it means is this. If I'm dealing with it in that way, then all I'm going to say is that I can easily be able to move right from a particular node and either come back to hit the same node, or I can move from that node and then will never come back and hit the same node. So what do we mean? All I'm saying is that if I start from a node A, then I move to other nodes and I come back to end up at node A, then that is what we are referring to as what? A closed walk or a cycle. Please, do you understand that?
Yes, sir.
Good. So in that case, the node that I started with, I'll come back and hit it. Now, in the case whereby I start with the same node A, and I move across different nodes, and I don't come back to end at the same node A, then that is basically what we're referring to as acyclic. Acyclic means when I start at node A, I will never come back and hit node A. Please, are we okay? Okay. So what are we trying to establish? We're trying to establish the fact that if I have undirected acyclic graph and I have a directed acyclic graph, then I can be able to say that all these two cases, right, no matter what it entails, I will never come back and hit at the same node I started with. So where then will the tree lie? A tree, we know, is a type of graph, but what kind of type of graph? In this case, we are going to know that it is actually a very typical example of an acyclic graph. But if you look at it very well, you realize that if you want to be able to classify the tree I've looked at, then we can say that the tree basically will fall in the realm of what? An undirected acyclic graph like this. Please, you understand? Jonathan, stop writing on my screen.
Sir, please, so
Yes.
Yes, sir. Yeah.
can you do some examples or some solving so that we can see, we can
I've not
understand it well?
gotten a place that I have to write on the screen. This one is you can see. You can see.
Yeah,
So
okay.
this is a typical example of what?
So this point up to this point is understandable.
Yeah, so don't worry, you get to a place you have to write, okay?
Okay, sir.
Okay, but I'll skip some parts because I'm not going to examine you on. When you get to second year, you're going to go into details of data structures. But this one, I'm just going to deal with the surfaces of it. Are we good? So please don't worry when I get to some place and I skip. Are we good? Because you will visit them again when you are doing data structures. Are we okay?
Okay, sir.
Okay.
Okay, sir.
So for the adjacency matrix, ways we can actually be able to look at it in terms of this particular graph, right? So one possible way of representing graphs is by using a two-dimensional array or matrix for storing the edges. So that's where the adjacency matrix comes in. So the adjacency matrix will help us to be able to store the various edges in that particular graph. So in this case, I can be able to have a 2 by 2 dimensional matrix. In this case, I'm just going to be able to index all the vertices A, B, C, D, starting from index 0, right? So A will be 0, B will be 1, all the way to H, which is 7. So I'm going to enable them as this. So this is A, B, C, D, E, F, G, H. A, B, C, D, F, G, H. These are the vertices. So you can see that. So these are the respective values there. But there's no self loop on it. Can you see that? So that's why here is 0. Okay. What about connection between A and B? Remember, A is 0, B is 1. Is there any connection between A and B? In other words, 0 and 1? Yes, there is. So that's
Yes.
a 1. Is there any connection between 0 and 2? In other words, A and C? Yes, there is. So that's why here is 1. Is there any connection between 0 and then 3? Yes, there
Yes.
is. Is there any connection between 0 and 4? In other words, A and E? No, there's no connection. There's no direct connection.
Yes.
That's why here is 0. All the way to hit the end. Can you see that? Now let's take the last one. Is there any connection between 0 and then 5? 0 and then 5? No. So that's why here it says. Now when it comes to B and then A, in other words, 1 and 0. 1 and 0, there's a connection. That's why here is 1. What about 1 and itself? Okay, 1 and itself, no. So there's no self loop here. What about 1 and then 2? No. So that's why there's a 0 here. What about 1 and 3? No. That's why there's a 0 here. What about 1 and 4? Yes. That's why there's a 1. So you do that to be able to get the adjacency matrix. Are we okay on that?
Yes, sir. Yes, sir.
So the adjacency matrix help you to be able to store the edges or the arcs. So skip this guy. Oh, please stop writing on my screen. Okay. All right. Then we look at the adjacency list. So the adjacency list basically will help us to be able to store the various what we refer to as the vertices, okay, in that particular case. So adjacency list is best suitable for sparse graphs. Once you know sparse graphs, please note. So the sparse graph is basically a graph whereby there is less number of edges. Okay, in other words, the edges are closer to the number of vertices in that particular graph. And the dense graph will have the edges be more in that particular graph. You can forget about the time complexity and space complexity for now. When you get into the data structures into details, you'll be worked into it. But for the time complexity and space complexity, there are 3 main factors you can consider. We have the best case, the worst case, and the average case scenario. Okay, so in this situation, we are interested in the worst case scenario. That the worst case scenario, can we be able to get the algorithm solve the problem for us or not? That's it. Okay. So the adjacency list help us to be able to get the vertices. Adjacency matrix help us to be able to get the edges. Are we good? Now let's look at the ADT quickly. So if we go to the ADT, we're going to have the instances of operations. Okay, so in terms of the instances, we're looking at it in terms of collection of elements, which is referred to as the nodes of vertices, and edges. Both edges and vertices may be associated with some values as well. Okay. Now let's look at the operation. So we're going to look at adjacent. When we say adjacent, then what we are saying is your neighbor, your direct neighbor. Okay. So let's say you're in a compound house, you are numbered 1, 2, 3, 4, 5. And let's say you are number 3. So your adjacent neighbor is the 4 and then the 2. They are the direct one you share a boundary with. Please, do you understand adjacency?
Yes, sir.
Okay. But we cannot say that your other if you are 3, then your adjacent neighbor should be 5. No, it's not possible because there is a 4 between you, the 3, and then the 5. Okay, so when you talk of adjacency, we are looking at someone you share boundary with. That's it. Are we good?
Yes, sir.
Yes, sir.
Okay, good. Now we come here. Test whether there is an edge from the vertex X to Y. Okay, so what we are saying is I want to be able to see whether there's a direct edge between X and Y, and this is the graph chain. Then the neighbors will list all the vertices directly connected to X. So in the case that I just gave, I have 1, 2, 3, 4. Okay, and then I'm trying to be able to find the neighbors of 3. The neighbors of 3 basically is going to deal with 4 and then 2. That's it. Then we can also have what we call the add vectors. So we're going to add X to the graph. So add the vertex X or the node X to the graph. If it's not present, okay, then you have to add it. But once it's present, we don't need to add it again. So once it is present, it will prompt you that that particular node X is already in the scene, so don't add it. Then now we can now also look at what we call the remove vertex X. If add is adding on, remove or delete. Then we can now go ahead to also look at what we refer to as the add edge. So the edge is always going to be the connection between 2 vertices, X and Y in this case. So I'm going to add XY, which is an edge, to the graph. Again, I'm going to also remove XY from the graph. Then I'm going to have get vertex value, right? So this is going to return the value associated with the vertex X. So let's say the vertex X probably is 24, right? I want to be able to return it. So I'm going to be able to get the vertex value J, then I'll specify the name of the node and it will return the value inside for me. Then I'm going to set the vertex value JXV. What basically is saying is this. The vertex value initially we say it is X. I want to be able to replace it with a V. So assuming that X was initially like 12 and I want to be able to assign it with a 13, then I'm going to replace the 12 with a 13. That's it. Get edge value. So we're going to return the value associated with the edge XY. Then set edge value. I'm going to identify the edge XY and I'm going to identify a value to it to say VIN. Then the last one has to do with what depth first, which will return the depth first traversal, breadth first, which will return the breadth first traversal. I'm going to look at it shortly with you. So the main thing has to do with what if I meant a problem whereby we should be able to get what we call the reachability problem. So reachability problem is whereby I should be able to start with a particular node and then hit a particular destinated node. So that's it about the reachability problem. Now, in simple form, reachability problem requires us to determine whether there exists a path in the given graph such that this path starts at the vertex V and supposed to end at the vertex U. So once I'm at the vertex V, I should be able to get a reachability aspect to U by navigating through a sort of possible path to hit me to U. Now it becomes a problem when I'm dealing with what a directed graph whereby in some instances the arrow does not point to U and I should be at a tight corner. That's also another key thing that we need to be able to identify on the table. Okay. We move on to be able to look at the more general form is to determine this. Okay, fine. The second problem is that. So there are two main ways, right? The first way is what we refer to as what? breadth-first traversal. The second one is what we call the depth-first traversal. So let's look at them in details. We start with the breadth-first search. Now, for the breadth-first search, simply put, the CD code is very interesting, okay? So we're going to start with the vertex vein and mark it as visited. Then all visited vertices adjacent from vein are basically going to be the next visits. We're going to deal with what we call the queue structure. So the queue structure, once I'm at a particular vein, I want to be able to identify the adjacent nodes or the neighbors of the vein. Then I put them at the back of the queue, so that as I'm moving on, it's supposed to keep track of them for me. That's basically what's going to happen. So let's see how we can understand this, okay? So please, everyone, pay attention to this part for me, okay? So start with this algorithm. Now, the queue, which is a linear data structure, make use of what we refer to as an enqueue. Enqueue means I are adding a particular node, okay, to the queue. So take it in a simple way. You're going to be able to buy food, right? You join it, you go, there's a queue. You don't go and stand in front. Is that it, guys? You stand at the back, right? That's what happens.
Yes, sir.
Yes, it's not about.
No, but so once you start at the back, you wait till it's your turn. That's a queue. The same way too, if you are going to do some transaction at the bank, you go, there is a queue. You don't go and stand in front, unless probably you have protocol, but you don't do that. You stand at the back. So standing at the back to join the queue is what we refer to as enqueue. Now, when it is at your turn and you are being served with your food, or you are being served with by the teller, it means that we are deleting you from the queue. And that's what we refer to as the queue. Please, are you okay?
Yes, sir.
Good. Now, in that case,
Yes, sir.
sorted out, I am now going to say that I'm going to.
No.
Isn't okay?
Sir, please take it again, please.
Please stop writing on the screen. So what I'm saying is that when you go to the bank and you're going to buy something, okay? So you're going to do a transaction, for example. If there's a queue in front of teller one, okay, and it's only teller one who can attend to your payment of fees, you don't go and stand in front of the people you stand at the back. Is that not it? The one who,
Yes, sir.
so once you stand at the back, it's the process is referred to as enqueuing. We are adding you at the end, the tail end, or the real end of the queue. So that's enqueue.
Oh,
On the screen. Then the dequeuing is when it is your time or your turn. Then you are being served. It means that you are going to be removed from the queue and go your way. So that's what we refer to as the queue. Understand the terminology now, right?
Yes, sir.
Yes, sir.
Good. With that terminology, then we can explain these algorithms. So algorithm BFS, okay? It means I'm going to have a graph. I'm going to have a particular vein. And the J and the vein are what we refer to as. Who can tell me? If you remember when we did with functions in session 6. What is G and F? A G and vein, sorry, here.
So the domain and the range.
Hey, no.
Is it domain and codomain?
Hey, no.
Okay.
Is anyone? The function of BFS. J and vein. What's the terminology? What or how do you refer to it?
Can I try again?
Yes, please, go ahead.
Say, are they the elements?
No, I'll not give it to you on that. No, they are not coordinates. Okay, so basically they are the parameters. Okay, so the function name is enqueue. Oh, sorry, BFS. Sorry, and then we can have the parameters at J and V.
Sir, please, what's the meaning of the BFS? I know the B is binary.
Breadth-first search. Yeah.
Okay.
Okay, thank you.
Thank you.
Now let's come in here. So we start with the first code. The first line is enqueue. So you are going to add V to the queue. Okay. So like you have gone and then you are going to join a queue for you to be served. Are we good? So you're going to add you by enqueuing you to the tail end of the queue. Now let's move on. So the second line says that once you are added on, is that particular node visited? If it is visited, yes, that's true. If it's not visited, then we have an issue. So I'm going to explain to you. So let's say that the vein which was added is now visited. It's true. While kill, which is a queue, is not empty, we are now going to dequeue kill. Dequeue kill means that I am going to remove the first element in front of the queue. So picture it in a nice way.
Which
You
is
go to the bank, you join at the back. There are about 5 people, okay? Once you join at the back, it has not reached your turn. Once it reaches your turn, you have to be dequeued. You have to be removed. I hope you understand.
yes, sir.
Good. Now, U equals to the queue. It means that we have removed you from the queue. Now, once you're removing it from the queue, this is what we do. For all the vertices W adjacent from U, in other words, all the adjacent nodes close to you, okay, before we remove you, let's assume that there are some people on the left, there are some people on the right who are probably your friends that they want to be able to get into your, for you to be able to sort them out. Maybe you went with your friends, and instead of your friends joining the queue, they said they will not join, they were standing beside you. Okay, so what happens is that once we remove you, we first identify those friends who share the same edge with you. So for all vertices W adjacent from U, if visited W is false, they have not been attended to because they were not in the queue. If visited is false, then what do? We say, hey guys, go and join the queue. We enqueue them at the back of the queue. Why? Because they were not standing in the line. They were beside. So because they have not been visited, we need to move them. The security guard will tell them to go and join the back of the queue. So we enqueue them. Now they go to the tail end. Does it make sense, guys?
It makes sense.
Yes, sir, it makes sense.
We're going to
Yes.
look at the practical example, then you understand it in that way.
Okay.
So visited W will now be true. So now what do we do? Now let's go ahead and look at the typical example. So that's what I'm talking about. So let's say that you are the first person, right? That you are in front of the queue. So once we put you to be served, okay, all we are going to do is that I'm going to identify your adjacent node, B and S. They are your friends. They are people who are the side of you. Then we put them at the tail end of the queue. The security guys say, hey, guys, go to the tail end of the queue. They went there. Now, once they went there, what do we have to do? We are now going to move you out. So you have moved. So this guy's out. A is now out. Okay, so we put A as a first out. Then we put B and S at the tail end of the queue. Meaning that when I'm done with A, because it's going to be in the sequential order, alphabetical order, we assume that B will come before A. So I'm going to attend to B. Now, if I'm attending to B, I need to check whether B has any adjacent friends. B doesn't have anyone. It's only A, but A is already marked and served. So I don't need to come and put A back again in the queue. You understand that? Because A is already served. So I can exit B directly. So B now goes. Okay. Now once B goes, the next person in the queue is basically S, this guy. So when I pick S, all I'm going to do is that, hey, S, I'm here to visit you. Do you have any friends before I serve you? S said, yes, I have 2 friends standing beside me, C and J. Oh, okay, I cannot serve C and J now. So go and put them at the back of the queue. So now C goes to the back of the queue. Then J also go to the back of the queue. Then I serve S. That means that S is outputted. Guys, we good?
Yes,
Very
sir.
good. Very good.
Good. Now, the next person in the queue, S is gone. So I come to C. Are we good? Now, when I pick C, I need to check the adjacent friends of C. And the adjacent friends of C are D, E, and F in alphabetical order. So I'm going to put them at the back of the queue. So I'm going to have D,
F.
E, and lastly F. Okay? Now, once we have this, then the next thing I'm going to do is I'm going to now say that, hey, C is your thing, go away. C goes. You come and join the output. I've already put D, E, and F at the back of the queue. Because C is gone, the next person on the table is J in the queue. He is supposed to be served. So I go to J, and I ask J, J, do you have any friend? He said, yes, I have friends. My friends I have R, F, H, and then who else? S. But this is a case that S and C are already served. So the security guy say, okay, now F and H, F is already in the queue. Okay, so I can now put H inside the queue. Are we good? So now in that case, all I'm going to do is that I'm going to now identify the H because F is already there and add H to the queue. Then I can say bye-bye to Jane. I dequeue Jane. Then the next person on the queue after dequeuing Jane is D. D for dog. So I go to the D. D, are you having any friend? No, I don't have any friend. My friend is already served. So D goes away. Then the next person in the queue basically is E. E for elephant. So I come and check E. E, do you have any friends? I have C as a friend. I also have H. C is already served. C is out. So H now is the one to be served. So in that case, once H is going to go into the queue, I have to check whether H is there. Oh, H is already in the queue, so I don't need to waste my time. So now I serve E. E goes away. Then I can now come to the next guy, which is F. So F2, all the adjacent friends of F are gone. So now F can be served without putting anything back again in the queue. Then lastly, I come to H. No other friend, which is unique because E and J are already served. So now H goes away. Please, any question?
Please, my question is, are you supposed to do it like in, how do I even say it? Like how you've done it, or you can do it anyhow.
Oh, anyhow you do, once you understand the
Yeah,
concept,
like the order.
Yeah, are you supposed to do it in?
order, you have to do it in that way, in that sequential order. So like the B and S, you can put S first, follow the
Yeah.
alphabetical order concept.
Okay.
This you understand?
So it means that you must do it alphabetically,
Yes,
right?
please. Yeah.
Okay.
If those are numbers, you should do it in that numerical form. The
Okay,
least number
so
of reference before the highest number. Okay, so
yeah,
that's the
so do it,
BFA.
okay.
Okay.
Sir.
Yeah.
So please. You check for the C before you tackle the S. Like the output, it has A, B, S. Why not A, B, C? Because C comes before S.
A's friend is not C. If A was
Okay.
connected to C, then
Oh.
go to B, C.
Okay, sir. Okay.
Is you understand?
Yes, sir. Yes.
Okay, great.
Yeah.
Hey,
Sir,
Yeah.
So I mean, the friends become the keys.
Yeah, the friends become the key. Okay. The ones they share
Yes.
direct back. Yes.
Generally,
Oh, okay.
is it always in algorithm?
Sorry, come again.
Generally, is it always in algorithm? Are you always evident on algorithm?
Yes. So we just did one. This is still the code. So we can actually write the code to implement this. But for this class, we don't do that. I will let you do that when you go to data structures. What I want from this class is how you can implement functions. That's all. That'll be good.
Yeah, good.
Yes,
Sir,
so
please, can you take it for the last time?
I will give you some. There are some examples down. So maybe when we get there, we can recap it. Okay.
Yes, that will be better, sir.
Right.
The
Let's-
examples.
Yeah.
So let's go on to the BFS. Sorry, the DFS, depth first search. Now, the depth first search will implement what we call a stack, right? So the stack basically is a linear data structure whereby basically, let's look at it in a real life scenario. You go to the kitchen, right? And then at the kitchen, let's say that your mother has a particular stack of plates, okay? So what happens is that your mother will have a number of plates. When she wash, she put it on top. She put it on top. She put it on top. So there's something I should have mentioned. With regard to the queue, we have something we call first in, first out. Okay? So in other words, the first person who joined the queue be the first person to be able to serve. Are we okay? Then we also have what we refer to as the last in, first serve. Now, the first in, first out, which we call the FIFO, is what is implemented in the queue. Okay, data structure. So when I go to the bank and I'm the first person, sometimes you go to bank, sometimes the bank opens at 8:30. You can see that around 8:15 a.m. people are queuing. They want to be the first people to be served. So once the door is open, at this situation, they are the first. Even the NIs, sometimes when you go there, there is some, I don't know, those times, I don't know what they're still doing it. They give some checks stuff, I don't know. Then there's places that they give you a check, they say that you're the first person you came and other stuff. Okay, that's it. So that's it about how the queue structure works. But the stack structure is a different thing altogether. That one is the last person who comes in will be the first person to be served. What does it mean? So you go to the kitchen like I'm talking about, and then we have stack of plates. And at the end, the last plate your mother put on the top, okay, will be the first plate she has to remove to serve your father. But I will not come and remove the plate, which is first thing that was down there. Because if you doesn't take care, she might end up having all the plates what pouring down and breaking. So in terms of the DFS, we implement what we refer to as the stack data structure, whereby the last plate will be the first to be served. In other words, the last in, first served. LIFO. Okay? Now, a depth first search of a graph differs from the BFS in that the exploration of a vertex vein is suspended as soon as a new vertex U is reached. So once we identify a new vertex U, we stop the others and we attend to that person. That's it. That's why we are saying that the last guy who comes in will preempt the people already in the queue to be made room for. At this time, the exploration of the new vertex U begins. When this new vertex has been explored, we continue to the vein, the one which we already continue with. The search terminates when all rich vertices have been fully explored, whereas in BFS, a node is fully explored before the exploration of any other node begins. So what does it mean? Let's look at it in a real life situation. Let's assume that you have a friend, okay? And then you are trying to be able to understand your friend. And then the friend you are trying to understand has other friends. Okay, so once you are trying to identify the friend, you make inquiries from other friends of your friend. Then from nowhere, okay, you met a new friend. Then you forget about the friend you are trying to explore. Then you now stick to that person. That's it. So maybe typical example is a funny way in terms of relationship, right? You're trying to be able to have a friend to date, right? For example, then from nowhere, you met a friend of his, then now you stop the one you are dating and go and follow that person. Indirectly, that's how the DFS works. Let's go into details and I'll explain that to you here. So you're going to be able to look at it in this way. So the pseudo code is very simple. So visited vein is true. Once I visited a particular node, I'm currently at a particular node, and it's true. Then for each vertex W adjacent from vein, right? For the friend of vein, okay, then what am I going to do? If that particular friend is not visited, then I have to apply the same DFS again on that particular friend, which is here to be visited. So what are we trying to say? All we are trying to say is that in a layman's understanding, when I'm at a particular node and I'm visiting the person, I start exploring like the BFS. If I meet a particular node, I stop the process of how the BFS will go to explore in depth. But rather, once I am there and I identify another friend of his, I stop all the other friends and I have to finish him. It doesn't really make sense, but this is what it makes. Let's go here and then see what happens. Maybe this algorithm will bring it up. Then I'll go to example, real life, then we understand. So you're going to see that the DFS with Jane and Vane, all we are saying is that the DFS is basically the method or the function name. And at the end, I am now going to look at it in terms of parameters or the variables. The variables or the parameters in this case is Jane and then Vane. Okay. Now let's start. What we're going to do, we're going to be able to say that we're going to push the vein into the stack. Okay. So once vein is pushed into the stack, it's at the top of the stack down. Are you seeing that? Now, visited vein is true because it's the first person. So in terms of stack, sorry, let me say this. The same way with the key, we have what we call the key, whereby you add a particular element at the end of the tail end or the real end of the queue. And then the key, you try to also remove the element from the front of that particular queue. In terms of stack, we do what we refer to as a push and then the pop. So the push means that you are inserting an element. In other words, you are inserting the vein on top of the stack. Then we have what we refer to as the pop. The pop means that you are removing the vein from the stack. And then we have what we refer to as the top. The top will tell us the element at the topmost of the stack. That's it. Are we good? So these are the three things we use when you're dealing with the stack, okay? So push vein onto the stack. Visited vein is true. Once the vein is now on the stack, you'll be the first person to be visited. That's it. So visited vein is true. It means that I've already visited a vein that I placed on top of the stack. So vein is gone. Now, while S is not empty, right? The stack is no longer empty. There are plates inside. There are elements inside. Then I need to be able to identify who is at the topmost, okay? So I use the top to identify the vertex which is at the topmost of the stack. Then I'm going to be able to say that that particular topmost element, I'm going to identify him as U. Then now what do I need to do? I need to pop S. Pop S means that if I'm identified that the stack is not empty, there's element inside, I need to pop the U. Pop U means I'm going to service U. Okay. Now for all neighbors W of U in the graph, all the adjacent friends of U, right? Then they have not been visited. So if they are not being visited, then what am I going to do? I'm going to now push them on top of the existing stack, which already have elements inside. So push W on it. When I push the W on it, then I'm now going to visit the W. So visited W is equal to true. That's the work is done. So what am I trying to say? What I'm trying to say is that I'm trying to be able to have a stack full of vertices. Now, as I'm trying to be able to service a vertex, if I pick, let's say, a vertex A, once I pop the vertex A, okay, I need to check whether vertex A has friends. Once vertex A has friends, all I'm going to do is very simple. Bring those friends on top of the stack. So when I bring vertex B and then S, which are friends, okay, now I'm going to have B and S there. So what do? I pick the B, who is the first guy I put there. Now, when I'm going to pop B, I need to check whether B has friends. If B has friends and I pop B, I forgot about the S. Then what do? I'm now going to now insert the friends. In other words, push the friends of B onto the stack. Remember, S is still pending. Now, if I pick, let's say J as a friend of B, I pop B. If J also has a friend, I have to also service the friend of Jane. Remember, S is still in the pipeline. Until I finish fully exhausting of the friends of B, I can come to S. Capish? Are we good?
Yes, sir.
The class is too
Yeah, we
quiet.
need some examples.
Eh,
Let's
We
look
need
at
some
this.
examples.
Yeah, we're going to get an example. I'm going to give it.
Everyone is quiet.
Yeah, I can see. So let's escalate with the example. This
We are
example,
following.
please go ahead.
Everybody casa.
It is well. BBABD, everything before.
Yeah,
All right.
befa.
Oh, Befa, you'll be fine. Guys, you finish. All right. All right, let's start. Let's see how it works with this example. So the same example we use for the BFS, we're going to use the same example for DFS. Okay. So what do we do? Let's assume that the starting node to visit is A, like we did. Oh, guys, please stop working on the writing on the screen. Control screen is a better alpha. Okay. All right. We good. Now we're going to see this. We're going to start with the first node, which is A. Now, once I pick A from the pseudocode, I'm going to put A first. A is already placed on the stack. Okay. Once A is already on the stack, what do I have to do? I'm going to remove A and then rather put the friends of A into the stack. The friends of A, we have B. So in terms of this, you forget about the stack thing. Let's see how it works here in a nice way. So I'm going to first start with A. I visit A. Okay. And when I visit A has two friends. The friends of A are B and then S. In this case, the B and S of A, I'm going to start with a B. So this guy will be the first guy, followed by this. Now, so I move to the first friend of B. A is gone, B is gone. I said forget about the stack and try and understand here. Now, once I'm at B and I'm visiting B, I have to check whether B has any other friend. If B has no other friend, we are good. Then I can now come to look at the second friend of A, which is S. Now pick S as the third guy. Then I visit S. So S is going out. As S is going out, I have to look for the friends of S. What are the friends? The friends of S are C and J. Okay, but although C and J are the friends, I need to first target the first friend. In alphabetical order, C is the first guy. So I target the C. C being the first friend of S will be the next guy to visit. But don't forget this guy is pending. Okay. Now, when I go to C, I'm going to pop C out. But before I'm done with C, I realize that C also has three friends. So what do? I need to now go ahead and look at all the friends of C, which is, let's say, 4.1. Okay. 4.2 in the alphabetical order. Can you see that? And then the other friend is what? 4.3. So what do? All I'm going to do is that I can now go to the first friend of C, which is D. Visit that guy. In visiting D, I have to also check whether D has any friend. Oh, D doesn't have any friend. Okay, good. Then I come to the second friend of C, which is E. Then I visit E. If I visit E, I need to also check whether E has any other friend. Yes, E has a friend. That friend is this guy. So that guy becomes 5. Now, this guy, which is 5, interesting enough, I cannot go to 4.3 because I have to finish fully exhausting E. So in fully exhausting E, then I cannot go to H because that's a friend. Now, once I mark H, I have to check whether H has any friend. It brings me back again to look at that friend who was the second friend of S. So that guy becomes 6. There he goes. Now, what happens? In that case, I have to also check whether J has a friend. Yes, J has a friend. That guy is F. So I'm going to put a 7 here. And then now F is gone. Work is done. Did you see the cycle?
Yes, sir.
Please, please, can you go over
Yeah,
again?
Sir,
Go over
please,
again.
you said we should do it in alphabetical form, right? Right
That
here,
was talking
but
about
it's not in alphabetical form. Some of the alphabets are mixed. This is why
yeah.
Yeah,
John, please mute up.
We need to have
Okay. So I think your question is, you said it's in alphabetical order, but you're not seeing the alphabetical order well.
Sir, please, you said it should be in alphabetical order, but here it's not well arranged in alphabetical order. That's what I'm asking why.
Sir, hello.
we need to have
Sir,
Yes.
sir,
Order is just supposed to guide you
the rules.
which
Follow the
friend
rules.
start with. Not that you are supposed to have A, B, C, D, E. No, not that. The alphabetical order is supposed to tell that if you have, let's say, two friends of A, B, and S, don't go and start with S, start with the B.
okay. Doc, please, when you go to the C, you even numbered the friends of C, which is D, E, and F. But whilst you were attending to E, you left. Whilst you were attending to the friends of C, you left out F and came to H before going back to F. That was what got me confused.
Okay, so let me take that part again. So I'm going to
Uh-huh.
go about it again a different marker, right? So follow. Okay. Let me use green. So we're going to start with A, right? So this is the first guy we start with. Are we okay? Now this guy has how many friends? B and S. So far, so good, right? So I mark B and then S. So between B and S, who should I go to first?
B, sir.
B.
B, sir.
So by that's the alphabetical order I mentioned.
Yes, sir.
Right. So when I go to B, B now becomes the second node to visit.
Okay.
Okay.
Now when I'm at B, I'll never come to S until I'm fully done with B. So I check whether B has any friend. It doesn't have any friend. So A is gone. B is also gone.
Okay.
Now when I'm done, because I didn't see any other friend of B, I have to come over again to the second friend of A, which is S. So far, so good, right?
Yes, sir.
Yes, sir.
Now, when I come to S, okay, I am now going to make S be served. So the S now will now be served, and then I'm going to output S.
Okay.
By outputting S, all I'm going to do is I need to identify the two friends of S, which is E and J. In alphabetical order, I have to visit C, not J. Guys, you are following, right?
Yes,
Yes, sir.
please.
Yes, sir.
Very
So I
cool.
go to C, and then in visiting C, I have to now check the friends of C. The
Okay.
friends of C are D, let me write one here, E, two here, and then F. The last one is F, let me put three. Now, in alphabetical order, D, E, F, okay, D comes first.
Yes.
So I visit D. So now D is out. Now, before I move on, I have to check whether D has any other friend. I'm not seeing any friend of D. So the next thing I have to do is that come back to the second friend of C,
Okay.
which is not F. Now alphabetical order. So now I go to E, I visit E. Now in visiting E, before I can come to the next friend of C, I have to check whether E has any other friend. The one who got confused, please pay attention here. E has a friend called H. So that will have a higher priority than F.
Okay. Okay.
So now I come back to this guy, who is the H, and I visit the H. Now, before I can still go back again, even to the third friend of C, I have to check whether H has a friend.
Okay.
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 H has a friend called J. So I visit the J.
Okay.
I've still not hit the third friend of C, which is F.
In this
So what do I do? I have to check whether J has a friend. Yes, J has a friend called F. If I call S, but S is already visited, don't forget that. So I now can hit my F. And I find out whether F has any other friend. No, F doesn't have any other friend. Hey, then I have to come back to my C. But C's friend, which is the F, is already visited. So work is done.
Okay.
Very clear now, sir.
All right, I'll say. Sir,
Yes, go ahead.
please, I have some two questions to ask. Can I ask?
Go ahead, please.
Please, so it means that with the BFS, you will not attend to the friends immediately, as is in this BFS, right?
Yes. So in
So how will you know that when they give?
in BFS, you have two friends at a go, B and S. You are going to attend to B. When you are done, you come to S. So you're attending to the friends in BFS, B for boy, simultaneously. In DFS, you have to fully exhaust all the friends
Okay.
of one of them
Okay.
before you go to the next friend.
Okay.
So I want to ask the question. In BFS, if this was BFS, this is A having friends B and S. Assuming B already have friends, okay? In BFS, boy, right? I have to first turn to this guy when I come to S. In DFS, if let's say B has more friends, okay, connected. In DFS, D for dog, right? I will have to fully exhaust all the friends of B before I can think of coming to look at the second friend of A.
Okay. So how will you know if the question is DFS or is DFS?
Oh, it will be told. You'll be told. For example, traverse this graph using breadth-first search, or traverse this graph using depth-first search. In fact, you also be told the particular node you should start with.
All right.
Okay.
All right.
So I have a question. So that means S and H have one friend, that's J.
S and H has one friend. S and H. S doesn't have one friend. S has two friends.
Yeah, two friends rather. That's C and let me say Jane.
Yeah.
And
I think
now,
you meant to say mutual friend, G. Mutual.
yeah, mutual friend or something like that.
Okay, that's fine. So
Sir,
you are bringing
please, please, I want to ask a question.
Please go ahead.
Sir, please, assuming the S, it is B there. So does it mean that you have to finish that B or the whole of the thing before you come to the other one? Like assuming the A, B, S, and the S is assuming B is at the S position.
Assuming A is what?
Like we have A, B, S, right? A has a friend of B, S, right? So assuming the S side, there's B there.
There side there is B there.
Yeah, and the B side is S. So you have to finish the B side before you come back to.
Exactly. Yes, you have to do that. So you are saying that if B was where the S is and S was where the yes, you have to fully exhaust all the B friends in DFS. Okay. All right, that's good. So that's a very good observation. So because of time, I'll let you guys do this. Okay. So find the DFS output of the following graph. You are using A as a starting node. Okay. I'll send a slides to you in no time. Okay. Then you do the same for this one. Then you do the same also for this one. Very good. So that's your assignment.
Yes, sir.
Next, we're going to meet to
All
look
right,
at.
sir.
Okay. Now,
Okay, yes.
let's look at the various applications that we can think of. So when we look at the various applications, we are looking at it in this way. So application of graph, we can probably look at it that in terms of the data structures, I've explained that to you that we want to be able to understand how we can look at some algorithms like the Dijkstra search algorithm, like the Ford Forkensen algorithm to be able to make some kind of search inside those graphs. We can use the B trees to do that. Then one of the typical applications, please mute, is what we refer to as a social network, like what I was explaining to you as well as a what do you call it? Facebook works, okay? In terms of how you can be able to represent the connections between users. In this case, the users will become the vertices or the nodes, and then their relationships in terms of their edges. They are crucial basically when you are trying to understand the network dynamics. The same way you can sit down and then there can be some suggested friend requests, there can be some friends probably brought to your table. That is how we can actually be able to handle these situations. Okay. So it's very important when you want to be able to understand how the DFS works in terms of the graph structure. The another thing too, we can also look at it is the genomics. So genomics basically is used when you want to be able to check the genes. So I'll give you a typical example, right? During the COVID-19 era, okay, scientists were trying to find the DNA structure of the COVID virus, basically. So in terms of genomics, we want to be able to say that graphs are used to model that relationships between the various genes or the proteins, okay, such as the gene regulatory network. So the DNA structure are all based on the proteins, how we can be able to handle it. Once you're able to know the dynamic structure or the trajectory of how these virus is being moving in the structure, we can actually be able to see how best we can handle it. Then we have what we call the ecology. Ecology is whereby in terms of food webs and ecosystems interactions can be represented using graphs to study species interactions and environmental impacts. Okay, so that is it about the ecology. So we want to see how the food structure in terms of the food webs works. Then the routing. So routing to like the way we did with the trees, we can also be able to see how we can handle transportations, right? So right now, the railways in Ghana is not quite a number, right? If you go to some developed countries like places you can think of, US and other places in the Asian, we should be able to work on it in this way. How? We can be able to handle it in a nice way whereby we can even put train stations underground, right? So I'll tell you some fun thing that happened when I was doing my PhD in Hong Kong, right? So we realized that there's a place called Hongham. When I started a PhD, I realized that they've started digging some tunnel there. Within Jack, I can say Jack, they were able to be finished, and then we started using the train wheels under there. I was like, how? You see, so they can actually dig. Right now, the country is developed. We can still go deep down and dig in a nice way and still create a particular train station there. And then that can be done in train wheels there. So that's also part of how things can be done when it comes to routing. And we can only do that when we have some fair understanding of how the graph theory works. And then we can be able to monitorize through the places that we can pass through. Because there are some places you cannot be able to penetrate. If there are some crazy story buildings there, it means that there'll be much pressure on the land. But if there's nothing like that there, and probably there's a desert or some trees there, or we can even do the drilling and then get some anchorage in mountains, okay? That can let the train pass through the mountains. So these are things that can be done. Anyway, Ghana has not gotten there. You get there. Then we can also look at it in terms of the supply chain management. Okay, so in terms of supply chain management, you represent supply chains to optimize logistics, manage inventory, and reduce costs. All these things comes in when you want to be able to economize that. So there are a lot of initiatives the government is working on. So we can actually be able to leverage on some of these things. If you want to be able to see how best we can get with the farmers to come and help with the feeding program of the schools, right? We can actually leverage on that. How? the farmers are in the various places. So instead of buying the food directly from retailers or the market women, we can actually hit the farmers and buy it from there, and then route it straight into those who are doing the school feeding program, and they can actually be able to have a better, good encourage for our students, and that can work. So these are things we can actually be able to handle when we are dealing with the supply chain management. Then the molecular structure too can also be there. In the chemistry point of view, they can actually be able to have molecules where atoms and nodes, bond edges, aiding to be able to understand even the nuclear reactions and other stuff. They are all part of these graphs theory can understand. And then lastly, with regard to the market networks, you want to be able to have a market advantage or a competitive advantage over your peers. So you should be able to analyze the market interactions, okay, of your competitors, how the trading is going, how the goods and service provision is going, and how the financial networking is happening. Then you can actually be able to catapult on that and say, I want to be able to do a promotion and get some discounts and other things so that at the end you can get more clients on the table. That's it. So basically, that's how it works when you're dealing with graphs. So at the end, we have been able to understand the graph in terms of this way. Basically, graphs are basically a defined set of what vertices and then edges, okay? And then at the end, we also saw that they are the directed, undirected graphs, the weighted and then the unweighted. Then we also saw the fact that the tree is a type of a graph, but basically it's a type of what acyclic graph. And then at the end, we also were looking at the properties. We came to also look at the various types of graph traversal. This is just a common ones. You can actually be able to leverage more on that when you get into their structures. They also saw some applications. So the BFS, the DFS we saw. BFS, you can visit the nodes simultaneously. DFS, of course, you have to start the alphabetical order or the one that comes first. Then the DFS, you can actually be able to visit the nodes by first checking the one which basically is the first friend, and then look at all the friends of that. That's it. Any questions?
Sir, please, I have a question.
Just go ahead.
Sir, please, can you go by that GF? Is it that one is the first in, first out, or the FIFO or the LIFO? No, the last part. I mean this one. GFS. Is it the LIFO or the FIFO?
So this one is the last in, first out, LIFO.
Last in, first out, LIFO, right? Okay.
Yeah.
And the other one is the FIFO, right?
Yes. First in, first out.
Okay.
Are you okay? Please, any other question?
Hello, sir.
Yes, please go
ahead. Sir. Hello, sir.
Please, I can hear you. Go ahead.
Sir, last week, the assignment you gave us, you said you put it on Saka, you didn't put it.
Yes, I'll do that.
Okay.
So those of you join late, we might have a tutorial this Wednesday at 7 p.m. Okay, so Charles, remind me on Tuesday, God willing, on that. Okay.
Hello, sir.
Okay, sir.
Hello, sir.
Yes.
Are you there?
My question is on abstract data graph.
Abstract data types, not data graphs.
So I'll be happy if you could take me there then.
Time is up. You need ADT here.
I didn't actually get vector value, GS, and then get edge value.
Okay. Here, right? Get vectors value.
Yes.
So this one, if the vectors is, let's say, an X, we want to know what is in the X, the value inside. If the value is 24, it will return the 24 for you. Then set vectors value. Okay. Now this means that I'm going to identify a vertex X, and then I'm going to give it or assign a value of v to it. So let's say that the vectors x is there, it doesn't have any value. So I'm going to assign 24 to x. That's it. Then when I come to get edge value, the edge, the graph is xy. What is the value of the xy, right? Because x is always a connection between two vertices. So let's say the xy, the value in terms of the duration is 24. Okay, so it is going to get me that 24. Now the second one says that set xy, which is an edge xy, with a value of v. So although the value is, let's say, 24, I want to replace it with, let's say, 30. So the 30 will now replace 24. So now when I go to get edge value xy, it will no longer be 24, but rather 30. So that's the meaning of set edge value. Please, do you understand now?
Okay, sir. Okay, sir. Thank you, sir.
You're welcome. Okay, please, any other question? Time is up. All right. So I think I'll just have to upload it, and then you can have access to the materials and read. Next week, when we meet, I'll try and see whether we can finish with the 2 pending sessions left. Differential calculus and then integral calculus. That's differentiation and integration. Then I think we can end the sessions. Then we are done. Okay. Any question? If there's no question, I think we are good. I can end the session. Let me upload the slides on Sakai.